So I have anybody concerned with writing a reference sheet for the midterm? Do we feel comfortable, confident? Okay. All right. Let's just go ahead and get right into the last material for this Unit 2 test. Oh, also, we was talking about when we're going to take the midterm, and was thinking, let's see. So we are done. Man, some of those dates on Canvas could have been changed, because we're done after today for Unit 2, and then we have, let's spend next time as a review for the Unit 2 test. That sound good? And then on the 25th, we could do a final midterm review, if you'd like. And then the 27th, we could take the midterm. How do you feel? And you're going to be gone that week, right?
Yeah.
So you'll take it when you come back?
Yeah.
Okay, yeah. Everybody else, how you feeling? What would you rather do? Do you like the 2 days of review? Okay. All right. We'll plan on that then. Also, I changed the whiteboard a little bit. See if this is easier to see. Let me know. If it's worse, let me know right away. Okay, so midterm will be 6/27/24. That work? All right, let's go ahead and get started. So intermolecular forces is the last topic. And good definition, these are the forces that hold molecules together. Oh, I need to write a little bit bigger, don't I? So for example, if you have H2O, looks something like that, right? Is water held? How's water? Can you see individual atoms in water? No, it's all held together, right? So well, if we remember from last time, what part of this molecule is partially negative? You don't have to memorize it, but you have to know how to look it up. Oxygen?
Yeah.
Why?
Because it has 6 valence electrons.
Okay, it has more valence electrons, but that's not the reason. Yeah.
Well, because it's least electronegative. But I guess.
Or most
Yeah.
electronegative. Electronegativity is the ability to accept electrons, right? So oxygen wants the electrons more, so it's partial negative, and these hydrogens are partial positive. That's what makes water polar, right? Are we good? So if we have one water molecule here, how many do we really have?
One.
Just one of them?
3.
We have trillions of them, right? You can't just have one molecule, one atom of anything. You wouldn't see it. You wouldn't know you had it, right? So we're going to have more than one. We're going to have trillions of these things. So if we have another water molecule sitting by this water molecule, what part is going to be attracted to that oxygen?
The molecular space.
The partial positive, right? There's going to be a little bit of attraction there. It's not going to bond. It's not the same. So this right here is a covalent bond. And this part right here, whoops, is intermolecular force. Or I will call IMF to simplify it. Good? So it's just is it very strong? It's strong enough, but it's not strong, right? We could easily grab water and rip it apart, right? We can't grab a water molecule and rip it apart as easy, okay? So these bonds, the covalent bonds, are stronger than the intermolecular forces, and we'll call these ones are weaker. Are we good? You understand what an intermolecular force is? Okay? There are four of them that we need to know about. Okay? And I would write this down exactly how I have it. So I'm going to show you in terms of strength of force. And also on the right side, I will tell you in terms of increasing in melting point / boiling point. You guys seeing this okay? Is it better? Yeah. Okay, good. All right, the very first one, so we're going to start with the strongest. This one is ion. So what kind of compounds do you think have this kind of intermolecular force?
Like the electrovalent compound.
What? Electromagnetic compounds?
Ionic
Ionic
compound.
compounds. Good. Yeah, you're good. Yeah, I knew you was getting there. Yeah, these are for ionic compounds. And does it make sense that these guys have the strongest or the highest melting point or the highest boiling point? Right? Think about an ionic compound, salt. We eat it every day. Yeah, just anything. But let's just take regular salt that we eat every day. Yep, NaCl, sodium chloride. And it has a melting point of like 800 degrees Fahrenheit. Really high. Because the intermolecular force is so strong. It's hard to break them apart. You with me? You take water. Water is what kind of compound? Covalent compound. No metals in it, right? And its melting point is what? Try again. 0 degrees or 32 degrees Fahrenheit, right? So a lot lower. Okay? So if it's an ionic compound, it's ion-ion intermolecular force. Pretty straightforward. Okay. Next one is hydrogen bonding. And hydrogen bonding is for polar covalent compounds. But not all polar covalent compounds. What else? Why do we call it hydrogen bonding? Must have hydrogen in it, right? But not every compound with hydrogen will have hydrogen bonding. So it's when hydrogen is bonded directly to nitrogen or oxygen or fluorine. What's so special about nitrogen, oxygen, or fluorine? Look at your charts and see if you can tell me. They are nonmetals. But why not this one? That's a nonmetal. Carbon's a nonmetal. And if hydrogen's bonded to carbon, it's not hydrogen bonding. Diatomic? Good guess. This is also not, right? No, that's good. Anything else? Look at your charts. What chart have we been looking at lately a lot? Yeah. They're the most electronegative. These are the highest electronegative elements on the periodic table. Okay? So if hydrogen is directly bonded to nitrogen or oxygen or fluorine, then that compound has hydrogen bonding, which is the strongest covalent intermolecular force. Are we good? Any questions on that one? We'll do some examples. Okay, next we have dipole-dipole. And dipole-dipole is also for polar covalent compounds. And we'll just say the rest of them, right? If it's not hydrogen bonding and it's a polar molecule, then it's a dipole-dipole intermolecular force. Good? And the last one is London dispersion, sometimes just called dispersion force. Hello. And these are for nonpolar molecules, nonpolar covalent. These are the weakest. And they have the lowest melting point and boiling point. So if you're reading your book and you come across something called van der Waals forces, that's these ones right here. The covalent intermolecular forces. But I don't think I'll test you on that, so but if you see it, then you know what it's talking about. Am I writing large enough? This okay? All right, let's do some examples. So how do we tell how to determine the intermolecular force? Step one. We draw what? The Lewis structure. Are we all okay with drawing the Lewis structure? Can we do it in our sleep yet? When I was taking organic chemistry, we had to draw a lot of structures. And I remember when I was taking that class at home on my table, just papers and papers and papers of all these drawings. There's everywhere. It was just so ingrained in me that, and I'm not saying this to boast or brag or anything, but I didn't ever get a score like I got in that class. And how did I do it? I don't know if I ever told you guys. You guys ever, did I ever tell you this, my experience here? I made this for that class. So if you ever take organic chemistry, you should do something like this. And don't just write them, but study them. Know each one of these cards. And I did that, and I aced that class. Can I teach it to you right now? Probably not. It's been a while. But drawing the structures, just live it, breathe it, eat it, because you're going to need to know this for the rest of the semester. Okay, make sure we got this down. Okay, step 2. Is determine the molecular geometry. Well, this sounds already something we've already done, right? So do we have to worry about the electron geometry so much? No, we just need to know the molecular geometry. Will we be tested on the electron geometry? Yes. If you have that sheet, you're golden. If you know how to read that reference sheet. Did you get a reference sheet? Yeah. Okay. Determine molecular geometry. Step 3 is determine if compound is polar or not. And then step 4, if we want to step 4, is classify the type of intermolecular force. And how do we do that? If it's an ionic compound, then what is it? What is it called? Ion-ion intermolecular force, right? Good? What kind of intermolecular force is it for a non-polar covalent compound? Look at your notes. Did we write it down? Maybe you should write this down, ladies and gentlemen. Dispersion force, right? So just follow this. If you don't want to have to memorize that right away, put it on your reference sheet. Good? But if some of you are going further on than this class in chemistry, I would highly recommend you knowing this stuff, okay? If you just need the generals and you want to move on and you're never going to ever do this stuff, then learn how to make a good reference sheet, because you get one, right? Okay. So let's do this. Let's do an example. NH3. Oh, I think Vitter's going to tell me what it is before he even does it. Yeah, what is it? Okay, you tell me what intermolecular force is it? It is a covalent compound, so we know it's not ion-ion, right? We can just take that out. No, I was just teasing when I said that, but let's work through it. Work through the steps. What's our first step?
Draw the Lewis structure.
Draw the Lewis structure. And if we've been drawing these and drawing these and drawing these, and we just say, I already know what the geometry is. Can we just skip to the geometry? If you know it. But you better be sure you know it. So take the time and draw it. So we got, what do we got to do to draw this thing? What's our first step in drawing a Lewis structure? Yeah, go ahead.
Count the valence.
Count the valence electrons. Good. So nitrogen has how many? Look at your periodic table. 5. Hydrogen has how many?
1.
1, and there's 3 of them, so that's a total of 3. We have 8 valence electrons. Okay? Now what? Nitrogen is the central atom because hydrogen is never the central atom. 2, 4, 6. We have 2 left. They go right on nitrogen. Do they all follow the octet? Okay. Now we got to determine the geometry. Don't stop here and think if you can know if it's polar by just looking at this. Go ahead.
Molecular shape for this is going to be bent.
Bent. What do you guys think?
I'm so sorry, it's trigonal pyramid.
Yep. Yeah, it's okay. I appreciate your trying for it. Okay. Now, she says it's bent or trigonal pyramid. How do we do this? Do you guys remember how to read this chart? We have 3 bonded atoms, 1 lone pair. So yeah, it is trigonal pyramid. And if you can't, I keep forgetting to bring these molecules, guys. Can you guys see what these look like in your mind? I will bring them next time for our review, because I do have to go to school tomorrow. I'll grab them, I hope. And would it help to have these on the midterm? Like on the table up here, you can come and look at if you want. Okay? I'll have these up here. They won't be labeled, but just so that you can see them. All right. What's our next step? We know what the geometry is, trigonal pyramid. Now what? Yeah, determine if the bond is polar or nonpolar. So hydrogen, nitrogen bound, that bond, that's the only bond there. Is it polar? What's the difference? 0.9 or something? What, 3.0 and 2.1? Yeah, 0.9. So it is polar. So we have to determine which side is partial positive, which side is partial negative, right? Which one is partial negative? Nitrogen or hydrogen? What? So Vita's got this. What about everybody else?
So you look at the,
Electronegativity chart,
and whichever one is more electronegative is the negative.
That's right. Do you understand?
Yes.
Okay. So that's partial positive, partial positive, partial positive. And how do you tell if it's polar? If it has lone pairs, there you go. It has a lone pair around the central atom, so it's polar, right? So this is a polar molecule. Now we got two options. Dipole-dipole or hydrogen bonding. What is it? Hydrogen bonding because hydrogen is directly bonded to nitrogen. Directly. So for example, if I had, let's say, a compound that looks like this. This is a polar molecule because we got lone pairs, right? Is this hydrogen bonding or dipole-dipole? You think dipole-dipole? Why? Doesn't matter if it has two lone pairs or one lone pair. Yeah.
It's bonded to two central atoms?
Nope, that's not why.
Because hydrogen's bonded to carbon.
Hydrogen is bonded to carbon, not oxygen, nitrogen, or fluorine. Has to be, even though there's hydrogen and oxygen in it, it doesn't mean it's hydrogen bonding. Has to be directly bonded to it. You with me? So this is dipole-dipole. And this one right here is hydrogen bonding, right? Questions? No questions?
I guess, could we go over how, could we go back to that, image we had of how to
Right
tell?
here?
Yeah.
Yeah, write this down. Make sure you have this. Does everybody have this on their sheet?
Do you think it would be possible to make a printout of it? That would probably take too long, right? It'd be better just.
I don't have one. I would have to make one, and this is made. Yeah, I'd just write it down.
Yeah.
I give you a lot of steps on how to do a lot of things, right? Don't get them confused. If you have to, write them on your reference sheet. Say, these are the steps to do this, these are the steps to do this, and so on. We're almost done with new material, guys. For today. Yeah, you don't have to know that, but if you read about it and you read about van der Waals forces, then you just know what they are. We good? Did you write down this arrow going up? That's the strength increases. And the arrow on the right, the melting point or the boiling point increases. Okay, ready to move on? Talk to me.
Yeah, I'm ready.
Okay. So let's do another one. Let's do SO2. I'm waiting for you guys to do it. We will do it, promise. But I want you to try it. So what's the point of doing this, all this stuff? So that we can determine the properties or have a best guess of what the properties would be like for different compounds. Okay. Or we can use it as a comparison to see which is higher melting point, lower melting point, and so on. Question?
Oh, not really a question. I just think I've solved it, but I'll
Okay.
wait for everybody else.
All right. You have an answer too? Okay. Who needs more time? Okay. Let's wait just a little bit longer. While you're waiting, we can go to this worksheet and do some more. On section 6, says tell what kind of intermolecular force the following compounds are subject to. So I'm talking about the worksheet that we got last time.
Oh,
But yeah, this paper right here is a midterm study guide.
still pretty helpful to have.
Yes. Okay,
When is the midterm again? Is it Thursday?
midterm is the 27th, is that what we said? Right here, 27th. So do a review next time for the Unit 2 test. And then on the 25th, we'll do a review for the midterm. And we'll, yeah. Okay, SO2. Who wants to tell me what type of intermolecular force SO2 has?
I
Go ahead,
believe-
Charlie.
I believe that it's dipole.
Dipole?
Mm-hmm.
What do you guys think? Dipole? Yes or no? No? What do you think?
London dispersion.
London dispersion? So we got two. What do you think?
Dispersion.
Dispersion force? All right, let's check it out. You think it's dipole? Oh, we got 50-50 here. Who wants to break the tie? What do you think? Dipole, dipole? Dipole, dipole? We got more people dipole, dipole. Should we just go with it? Well, let's figure it out, right? All right. So let's draw the structure. So they all have 6 valence electrons, sulfur and oxygen. They're in the same group, right? Have we counted wrong?
Yeah.
Be careful, that's the very first step. Don't mess it up on there. So we got 18 valence electrons. Central atom is sulfur. 2, 4. We have 14 left. 2, 4, 6, 8, 10, 12. We have 2 left. Has to go on the sulfur.
And because of the lone pair, that makes it polar?
That's right. So if we want to get right up there and say, okay, there's a double bond there. But we can see there's 3 regions, right? 2 bonded atoms and 1 lone pair. So this is bent. It looks like this. So this is a polar molecule. Well, what's the difference in sulfur and oxygen? Does it matter? Not really, because of this lone pair, right? But the difference is like what? It's like still 1, still pretty big. So this is partial positive, partial negative, partial negative. We can separate the positives from the negative. This is a polar molecule. Is it hydrogen bonding or dipole-dipole? There's no hydrogen there at all, so yeah, it's dipole-dipole. Perfect. Are we good? Find our mistake?
Mm-hmm.
It's good we're making mistakes here, not on the test, right?
Wonderful, yes.
Okay. Let's do... Should we do one that's on the midterm? BF3. Okay, what is this? London dispersion. What do you guys think? Y'all.
It's
Non-polar.
yeah.
No lone pairs, right? So even if we shared some of these and made it to be a double bond, which is not correct, even if we did that, it'd still be the same, wouldn't it? So in the end, do we really need to know that exception? Maybe not. Okay, so it's still non-polar. This is a covalent compound, so it's London dispersion or dispersion force. Good? What?
Why it is 45 minutes?
Probably a dude named, last name London discovered it or something. My guess. Or maybe it was discovered in London. I don't know.
So the main difference is if it's nonpolar, then the difference between dipole and London dispersion is the molecular geometry.
Well, dipole is a polar molecule.
Oh,
Hydrogen bonding is also a polar molecule. You need to know the difference between those two. What's the difference between London dispersion and dipole? Sorry, what's the difference between dipole and hydrogen bonding?
There are hydrogen in it, and there is no hydrogen in
Hydrogen directly bonded to nitrogen, oxygen, or fluorine, right?
okay.
Only those three.
Hmm.
If it's not, then it's dipole. In fact, hydrogen bonding is a type of dipole. Dipole means exactly what we said polar is. Positive on one side, negative on the other side. That's a dipole. Okay, that's what a dipole is. And so if we have positive on one side, negative on the other side, we say it's polar. So that's a dipole. Hydrogen bonding, compound that has hydrogen bonding is also a dipole. We just have a specific name for it because it happens quite regularly in our human bodies. And so we give it a special name. That's the only difference. Okay? Good? All right, let's do a little bit on this worksheet. And if you can tell me just by looking at it, and ladies and gentlemen, I'm not trying to get you to do this fast. I just want to see, can you look at this and tell me? So this is the worksheet from last time, section 6. On the back side, the very last two sections, section 6. Okay, it says, what kind of intermolecular force is LiI, lithium iodide? Can anybody tell me without doing anything? Yeah, what is it? Yeah, here you go. You need one from last time? It might have been 2 times ago that I gave it. Here you go. So on the back side, section 6, VI, lithium iodide, LiI. What kind of intermolecular force? Yeah. It is ionic compound, so it's ion-ion, right? Are we good? So if it's ionic compound, we're done. We don't have to draw a structure. We don't have to determine it's polar, because it's not. It's ionic. It's an ionic compound. Are we good? Okay, what about F2? Fluoride, or the fluorine gas. London dispersion. Why do you say it's London dispersion right away?
The fluorine is nonpolar.
Non-polar. How do you know it's non-polar right away?
Because the it's less than.
Yeah, the electronegativity difference is 0.
Yeah.
Fluorine and fluorine, there's 0 polar bonds. That means it's non-polar without even further looking at it further, right? So this is, what did you say it was?
Dispersion.
London dispersion force, right? And again, ladies and gents, you don't have to memorize this, but if you can look at things and maybe help you a little bit quicker, right? And again, we're not for speed, but if you can recognize things, things will flow better, it seems like, and you'll feel better about things. But go ahead and double check this. Draw it out. It's going to look like this. We can see, well, there's no difference, right? All right. What about HCN? Yeah. What? Hydrogen bonding. Why do you say hydrogen bonding? You say no? Hydrogen is not directly bonded to nitrogen. So
But it is
it's
to carbon.
okay, but for hydrogen bonding, hydrogen has to be directly bonded to nitrogen, oxygen, or fluorine. That's it. Are we good? So we can't say, oh, it has a hydrogen in it, must be hydrogen bonding. Are we good? Dipole, dipole? Why do you say dipole, dipole? Because it's the next best thing to guess. Let's not guess. If we don't know, we better draw it out. But this one is a little tricky, ladies and gentlemen. And possible test question right here. I've given you guys a sheet called the polyatomic ion list. Do you have that list? Do you have to memorize those? No, you don't. But you better look at it. You better be familiar with it.
Is this it?
Yeah. You better be familiar with it. What kind of compound is this?
A polyatomic ion?
It's not a polyatomic ion because there's no charge, but is there a polyatomic ion in it? Look at your polyatomic ion list. Is there a polyatomic ion in this compound?
Is it CN?
What's that called?
Hydrochloric acid?
What's CN called? Look at your list.
HCN.
But what, are you looking at your polyatomic ion list? Is CN minus on there?
Yes?
And what's that called?
Cyanide.
Cyanide. This is a polyatomic ion. What does that tell us about this compound? What kind of compound is this?
Ion?
It's an ionic compound. Therefore, the intermolecular force is ion-ion. You with me? So you do not have to memorize the polyatomic ion list, but you better have them handy and become familiar with them. Either that or just on every problem, look at it. Oh, does it have a polyatomic ion in it? Because there's no metals in that thing, but that's an ionic compound. Good? And we're not trying to trick you. This is real life stuff. This is a real compound. And so if we want to compare this compound with, let's say, water, we can if we understand it. But if we don't recognize that this is, right, then we'd say, oh, this must have a lower melting point than water. But what do you think? Higher melting point than water because it's an ionic compound. You with me? All right, let's go with C4H10. Who can tell me that right away? I gave you a little trick a time or two ago. If you look at this, you can know right away. And you don't have to know the trick. You can still draw it and figure it out, guys. You can still do the hard work and get it right. Don't have to memorize everything, promise. Does anybody know this little trick? What is it?
Is it non-polar because it's symmetrical?
Okay, how do you know it's symmetrical? I didn't even draw it.
Or if we were to draw?
Hey, yeah, you could draw it. You could draw it. Definitely could, and you can figure it out. What kind of elements are in this?
It's a non-polar.
Carbon, hydrogen compound.
Any hydrogen carbon.
If the compound is only carbon, hydrogen, it is non-polar. So this is London dispersion. Without even looking at it. I mean, you just look at it without even doing anything. But ladies and gents, you can figure it out. We can count the valence electrons. 4 times 4 is 16, plus 10, there's 26 electrons. There's 4 carbons bonded together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogens. Zero lone pairs. 0 polar bonds. It's still nonpolar. Good? So you don't have to memorize stuff. You really don't. But as you do this, if you practice and do a lot of these, you start to pick up on these little things. Say, oh yeah, those guys aren't polar ever, right? And remember, it has to be, if this is C3HAO, is that one polar? Yes, it is because of that guy right there. If it's only a carbon-hydrogen compound, only carbon-hydrogen, 0 polar bonds, but if that's bonded to either a hydrogen or a carbon, it's polar, right? But if you're not sure, draw it out. One, 2, 3, 4, 5, 6, 7, 8. There it is. Okay? There's our central atom. Because this part right here is nonpolar, right? There's no bonded atoms over, no polar bonds over there. So we're just interested in this one right here. Questions? All right. Let's what about H2O? What? London dispersion. What do you think?
Isn't it hydrogen?
Hydrogen bonding. Well, that depends if it's polar or nonpolar, right? Because if it just has H and O, and H has to be directly bonded to oxygen, so it looks like hydrogen bonding. Is it a polar bond? It is a polar molecule. So this is hydrogen bonding. Good. We have to know both of those things, right? But if hydrogen is directly bonded to nitrogen, oxygen, or fluorine, those are polar bonds. Unless it's 100% symmetrical, it is hydrogen bonding. But if it's hydrogen, chances are it's going to be polar. Okay? For those 3. In fact, I've never seen it not. I'm not going to say it, you can't. Because do we know everything in science? No, we don't. Okay? Are we good on determining if it's what type of intermolecular force it is? Okay, let's do this. Let's put these in order from lowest to highest in melting point. And if you feel like this is too much to chew right now, let me know and we'll do it. I just want to see, can you do this right now? Put these in order from lowest to highest melting point. And again, these are just predictions. Does everything follow the same pattern exactly? Well, it seems like there's always exceptions, right? So this is just a prediction. Most things in chemistry are predictions.
What is melting point, the highest melting point?
So start with the lowest and then go to the highest. Start with the lowest melting point. Start with the compound that has the lowest melting point. And then, right, the next one is the next lowest, the next one, until you get to the highest. Good? And read it on the test. It might say from highest to lowest. Just read it, right? Who can tell me the one with the lowest right now? Raise your hand if you can.
CH4.
Why CH4? Only carbon-hydrogen compounds, right? Nonpolar. This is London dispersion. That's our first step. Let's determine the intermolecular forces first. What intermolecular force does this one have? What is it?
Hydrogen.
Hydrogen bonding. What about this one? How do you know? Not lion. It has a metal in it, right? And what about this one here? We just did this one, right? Dipole. Okay. Which one's the lowest? London dispersion. So we got CH4. Then what's next? Dipole, so SO2. Then NH3, hydrogen bonding. And then sodium chloride. Does that make sense? There's a good test question right there. Let's do another one. Let's do another simple. You guys got this? Or should we go on to the next hardest one?
Let's do it one more.
One more? Okay. Okay, let's say we have Lowest to highest. Well, yeah, melting or boiling point, doesn't matter. They're the same. Let's do boiling point this time. It doesn't matter. It's all the same. Just kidding you, man. Besides beer, who can tell me the one with the lowest boiling point? Go ahead, Parker.
Is it C2H6?
What do you guys think? Is that the lowest?
HCN.
HCN. Those are our options. Who says it's H2 or C2H6? Who says it's HCN? Who says I have no idea? Okay. Then, rather than trying to just quickly do this, what do?
Write it out.
Find the intermolecular forces. What's the intermolecular force for H2S? What does that look like? Bent, right? So it's like this. Partial negative, partial positive, partial positive. Oh wait, what's the difference between sulfur and hydrogen? Oh, it's only 0.4. But what did we say? In the molecule, we're worried more about symmetry, right? So this is just slightly polar, but it's polar nonetheless, right? This is dipole-dipole. Okay, are we good? What about C2H6? This is nonpolar because, well, even if we draw it out, we can see carbon-hydrogen bonds. There's 0 polar bonds, right? So this is London dispersion. What about HCN? Oh, that's ion-ion. Because that has a polyatomic ion in it. What about water?
Hydrogen bonding.
Hydrogen bonding. If we draw it, looks just like H2S, right? It's still bent. Still polar, has lone pairs. But hydrogen is directly bonded to oxygen, so it's hydrogen bonding. So C2H6 is the lowest. Then H2S, then H2O, and then HCN. Are we good? So maybe we shouldn't just try to hurry and make it, right? And just guess. Draw them out. Make sure we know. Questions? Let's do another one. Harder one. Put this in order from lowest to highest melting or boiling point. What's the first step? Determine the intermolecular forces. What kind of intermolecular forces do we have here? They're all nonpolar. That means the intermolecular force is London dispersion, right?
Or is it?
Yeah, they're all London dispersion.
Oh,
They're all nonpolar.
so they're all in the same place?
They don't have the same melting point, boiling point. Everything, I mean, some things might have similar properties, but no compounds have the exact same properties. So what we do next, if they all have the same intermolecular force, we check what we call molar mass. We didn't learn this yet. We can call that atomic mass. But it's not an atom. Molecular mass. Right? The mass of the molecule. Do we know how to find the mass of the molecule?
Add the,
What's the mass of carbon? Look at your periodic table. 12.01.
Yes.
Can we just say that's 12? Or do we have to say it's 12.01? What do you think?
Just 12,
Why?
around
Well, why can we round?
what is more?
Yeah, go ahead.
Because the atomic mass includes the isotopes? Like
Yeah,
the
it's
average?
just an average, right? So who knows which isotopes we're dealing with? No one. And 12.01 is basically 12, right? You can use 12.01. In fact, here's the thing. If you're not sure if you should round, then don't. It's fine if you don't round. Sometimes you shouldn't round. And I'll show you cases where you shouldn't round. What's the mass for hydrogen?
2,
Look again.
1,
1.008, basically 1, right? Times 4 of them, that's 4. Add those together and that's 16. The book calls it AMUs, right? But we call it grams per mole. That's why we call it molar mass. It's the mass per mole. You get that? So this is a new idea. So there is the molar mass of that guy. What's the molar mass of C4H10? Is it more or less? Obviously more. Has 4 carbons compared to 1. And that one has 3 compared to 1. That one has 2 compared to 1. We can add these up if we want. 4 times 12 is 48, plus 10 is 58. Three times 12 is 36, plus 8 is 44. No. Yeah, 44. And this one here, 2 times 12. You guys understand where I'm getting my numbers?
24,
24 plus 6,
30.
30 grams per mole. Which one has the lowest molar mass? CH4. That means it has the lowest melting point. Then
C2H6.
C2H6. Then C3H8. Then C4H10. You guys want to know the names of these things?
I know methane.
Methane, ethane, propane, butane. Butane's the stuff in cigarette lighters. And ethane, if you turn it into an alcohol, it turns into what?
Ethanol.
Ethanol or moonshine. Right? Okay. We good? So if you only have to check the mass if they have the same
So
intermolecular forces
is ethanol what they have in like
in
alcohol?
gasoline.
Oh, okay. I was gonna say in like when they say ABV, that's
A-
alcohol. I think it's like alcohol volume per bottle.
I don't know actually on that, but ethanol is what they put in gasoline.
Mm.
You can get ethanol-free gas,
Mm.
but most gas has ethanol in it. This is the stuff back in the day, they called it moonshine. It was illegal, right? Well, it still is.
Made you blind?
Well, I don't know. It might, if you drink too much of it. Okay. Let's do one more, yeah? Uh-oh. One more. C2H6. Put these in order of lowest to highest boiling point. You have an answer? Okay. Don't worry about being the fast person in the room, because let me tell you from my experience, the people who get done first, they either have the best score or the worst score. Really. So I would really write it out. Make sure you're certain. Okay? Okay, what's the first step? What type of intermolecular force do we have? So, what is it for H2O? Hydrogen bonding. What is it for this? Yucky. Is it an ion? How do you know? How do you know it is? Oh, it has hydroxide? Ah, good guess. It doesn't have hydroxide. Now listen. If it looks like it has hydroxide in it, right? What's the other ion? Is this an ion? It's not. An ionic compound must be bonded together from a cation and an anion. Here, it looks like we have an anion, but we don't have a cation. Is hydrogen a cation? By itself it is. That's why HCN was. Okay? So this is not ion. Oh, making it so hard.
How are we even supposed to write this?
Like this. Isn't that the way that it looks? If it's a big compound like this is an organic chemical. And I'm not going to show you the names of this and how to write the structures really, but if I use this on the test, it's written how it's structured. Do you see that? So this is hydrogen here, 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 and here. Oh, something's wild with my... Is this hydrogen bonding? Yes. Hydrogen is directly bonded to oxygen, and if we draw all the valence electrons, those are going to have lone pairs there. This part and this part makes it polar.
So it's,
So this is hydrogen bonding. Whoa, what's going on?
so, and then we are trying to put it highest to lowest or lowest to highest?
What about CH4,
The lowest.
which is
London dispersion?
London dispersion? And C2H6,
London dispersion.
also London dispersion. So we got 2 hydrogen bondings and 2 London dispersion. So these, out of these 2, which one's the lowest? CH4. Then C2H6. Then out of these 2, which one's the lowest? H2O, because less mass, right? Do we even have to calculate the mass? We don't, because it has, we could just see that it has more oxygens and more hydrogens, right? This is going to be HOCH2CH2OH. Are we good? All right, I gotta take a little break. You guys want to take a break? We're almost done. Sorry. Any questions so far? So can we write steps to determine the lowest to highest melting point if we want? What's the first step?
Find the,
Yeah, find intermolecular force. Determine the intermolecular force, right? Then we can follow the steps. Ion is biggest, right? Then hydrogen bonding, then dipole, then London dispersion. All right, my thing is breaking up for some reason. I don't know why. But if they have the same intermolecular force, what do we do? have to have the same intermolecular force, then higher mass means higher melting point / boiling point. Are we good? I'm gonna leave you with one other thing to think about. We're gonna get more into this in Unit 3, but like dissolves, does dissolve have 2 S's in it? Yeah? Yeah. Dissolves like. What does that mean?
2 similar compounds will dissolve each other?
That's right. So how do you tell if it's like? Polar compounds dissolve in polar compounds, and nonpolar dissolves in nonpolar compounds. We'll talk more about how things dissolve, but we did a little bit already, yeah? So what about water is what kind of compound? Polar. So what kind of compound is oil?
Nonpolar.
It has to be nonpolar. We know it doesn't mix, right? In fact, oil and water is said to be what? Immiscible. You guys ever heard of that word? Means does not dissolve in any proportions. So if we have a drop of oil and throw it in the ocean, it's not going to dissolve, ever. That's immiscible.
If you do have sort of like a mediary compound, you can mix them together, and that's how they get vinaigrettes for salad dressings. But that's, by themselves, they won't mix. They
That's
need
right.
that third thing.
What's another example of this? How do you get oil off your pans? You just put it under water, right? And it'll just come off. And it stays all slimy, right? How do you get it off? I hope we all know this. Soap, right?
Oh.
Yeah, you put soap on it. Well, what's soap look like? Let me show you. So oil looks like this, where each one of these peaks and troughs, these guys are carbons, right? So these are our carbons. And then you have, it's just a carbon chain with hydrogens on it, right? But this is just the fast way to draw it, okay? So this is oil, just a big, long carbon chain. It might have other things in it as well, but there's mostly carbon chain, carbon hydrogens, okay? And soap looks like this. This carbon chain with a polar head. So this will dissolve this because it's like it, right? And what dissolves the polar part? Something else that's polar. Isn't that cool?
Yeah.
Okay. And so it'll all just kind of push it away. Kind of neat, huh? We'll talk more about that next unit when we talk about things that dissolve in each other. But that's good to know about right now because we're talking about polarity. Polar dissolves polar, nonpolar dissolves nonpolar. Questions? Oh, one more thing. I think we talked about this last time. Whoops. Which one is more polar? They're both polar compounds. They're both hydrogen bonding. Which one is more polar? What? No. So it's not this.
H2O because
Why?
of the difference between the electronegativity
That's right.
of oxygen and hydrogen.
That's it. This difference is what? 3.5 to 2.1. It's 1.4.
Mm-hmm.
And this difference here is 2.1 to 3. What is it?
That's going to be 1.4. Oh wait, they're the same.
Hold on. I did the math wrong then. Is this 1.4? Okay. Well,
Yeah.
so
Right,
3.5 minus 2.1.
Wait.
Yeah, that one's 1.4. And so this one is 3 minus 2.1 is only 0.9. There we go. Yeah.
Ah.
Right? So this one's a more polar molecule. So here's that's next unit. We'll talk about it next unit. But does that make sense how to tell if a compound is more polar versus another compound? More or less? All right. Okay, that's it. Are there any questions? So we worked a lot of examples on this worksheet. Anything else? Okay, well, we're done 20 minutes early. You guys okay with that? And so next time, come with questions. Study. Come with questions for Unit 2 test. So try to have Unit 2 test, practice test done, and come with questions next time. That way we can go over the questions that you have questions on, and not just something I thought about to go over. Does that make sense to everybody? The more questions you have, the more you're going to learn. And we can stay as long or as short as whatever we need next time. Well, at least until 7:20. But if you guys feel like you're golden, we're not going to cover any new stuff. But I would highly recommend that you study over the next couple of days and get questions ready. Or if you find that you don't have any questions, have a long weekend. Sound good? Okay. Have a great rest of your night and drive safe, please.